Welcome to Instrulogic channel and this video on PLC Basics. If you've ever wondered how industries automate machines and processes, you're in the right place. Today, we'll start with the foundation, understanding what a PLC is and why it's so important in modern automation. A Programmable Logic Controller, or PLC, is the brain behind industrial automation. It's a special type of computer designed to control machines like motors, pumps, and valves. Unlike regular computers, PLCs are built tough. They can handle heat, dust, vibration, and electrical noise in factories. On the screen, you can see different PLC units and a simple diagram showing how a PLC connects to input devices like sensors and push buttons, and output devices like motors and actuators. The PLC reads signals from sensors, processes them according to the programmed logic, and then sends commands to control equipment. Think about this. Every time you press a start button on a machine, something happens instantly. That's the PLC making decisions in milliseconds. Amazing, right? In the next part, we'll dive deeper into why PLCs replaced old relay-based systems and how they make automation easier and more reliable. Now, let's talk about an important question. Why did PLCs replace relay logic in industrial automation? Before PLCs, control systems were built using relay logic. These were physical relays wired together to perform logic operations. But there were major problems. Relay logic was bulky and complex. Imagine hundreds of relays mounted on panels with miles of wiring. Troubleshooting was hard. If something failed, finding the fault in that maze of wires was time-consuming. Modifications were a nightmare. Changing the logic meant rewiring the entire panel. PLCs solved all these issues. With a PLC, logic is implemented in software, not hardware. Need a change? Just edit the program. No rewiring required. Plus, PLCs are fast, reliable, and compact, making them the perfect choice for modern automation. Think about this. Would you rather spend hours rewiring a panel or just click a few buttons to update the logic? That's the power of PLCs. Next, we'll look at the main components of a PLC and understand how they work together. Now that we know why PLCs are important, let's look at the main components of a PLC system. A PLC is made up of several key parts. CPU, the brain of the system. This is where all the processing happens. It reads inputs, executes the logic, and sends commands to outputs. I/O modules, the interface with the real world. Inputs bring signals from sensors and switches, while outputs control devices like motors and valves. Power supply, typically 24 volts DC. This keeps the PLC running reliably. Communication ports, for programming and data exchange. These allow engineers to connect laptops or HMIs to configure and monitor the PLC. On the screen, you can see a typical PLC hardware layout. The power supply on one side, the CPU next to it, and then the I/O modules for digital and analog signals. Think about this. Without these components working together, automation would not be possible. Which part do you think is most critical? The CPU or the I/O modules? Share your thoughts in the comments. Next, we'll see how these components work together in a PLC scan cycle. Here is the simple block diagram of a PLC. Now let's understand how a PLC actually works. The process is called the scan cycle, and it happens continuously inside the PLC. The scan cycle has 4 main steps. 1 reads all inputs. The PLC checks the status of sensors, switches, and other input devices. 2. Executes user logic. It runs the program stored in its memory to make decisions. 3. Updates outputs accordingly. Based on the logic, it sends signals to actuators like motors, valves, or lamps. 4. Repeats continuously. This cycle happens over and over, very fast, often in milliseconds, so the system responds almost instantly. On the diagram, you can see how the input module sends data to the CPU processes it, and then the output module controls the machine or process. The power supply keeps everything running. Imagine this. Every time you press a start button, the PLC completes this entire cycle in a fraction of a second. That's why automation feels so smooth. Next, we'll look at some real-world examples of PLC logic in action. Let's look at a simple example of PLC logic. How to start a motor using a push button. Here's how it works. When you press the Start push button, the signal goes to the PLC as an input. The PLC checks the logic programmed inside. If the Start button is pressed, it energizes the output. That output signal activates the motor starter coil, which starts the motor. If you press the Stop button, the circuit breaks and the motor stops immediately. On the screen, you can see the ladder diagram for this logic. The Start button is represented as a normally open contact and the Stop button as a normally closed contact. When the start condition is true, the output coil turns on and the motor runs. This is the most basic PLC logic used in industries. Can you think of other machines where this start-stop concept is applied? Share your ideas in the comments. Next, we'll see another example. Automatic tank level control using PLC. Now let's look at another practical example. Automatic tank level control using a PLC. Here's how it works. A level sensor or switch gives input to the PLC, indicating the water level inside the tank. The PLC processes this signal and decides whether to open or close the inlet valve. This ensures automatic tank filling without manual intervention. Such systems are widely used in RO plants, water treatment facilities, and many industrial processes. On the diagram, you can see the ultrasonic sensor mounted on the tank, sending signals to the PLC through the input module. The PLC then controls the inlet valve via the output module, maintaining the desired water level. Think about this. Automation like this saves time, reduces errors, and improves efficiency. Where else do you think level control is important? Share your ideas in the comments. Next, we'll compare PLC-based control with traditional relay logic and see why PLCs are the preferred choice today. Now, let's quickly compare PLC-based control with traditional relay logic. In relay logic, every condition requires physical wiring. If you want to add a new feature, you need to add more relays and wires. In a PLC, logic is implemented in software. No extra wiring, just update the program. With relays, any modification means rewiring the entire panel, which is time-consuming and costly. With PLCs, modification is as simple as editing the program on your computer. This is why PLCs are faster, easier to maintain, and much more flexible compared to relay-based systems. Which one would you prefer for a modern factory? Hundreds of relays or a compact PLC with software logic? Share your thoughts in the comments. Next, we'll explore the different PLC programming languages used in automation. Now that we understand how PLCs work, let's talk about how we program them. PLCs use different programming languages, and knowing these is essential for automation engineers. The most common language is ladder logic. It looks like an electrical circuit diagram, which makes it easy for electricians and engineers to understand. Next is function block diagram, which uses blocks to represent functions and is great for process control. Then we have structured text, which is similar to high-level programming languages like Pascal or C. It's powerful for complex calculations and logic. Finally, there's instruction list, which is a low-level, text-based language, though it's less common today. Each language has its own advantages, and the choice depends on the application and the engineer's preference. Which language do you think is easiest to learn for beginners? Ladder logic or structured text? Drop your answer in the comments. Next, we'll see where PLCs are used in real-world applications. Finally, let's talk about where PLCs are used in real-world applications. You'll be surprised to know they are everywhere in automation. PLCs are commonly found in water treatment plants, controlling pumps, valves, and chemical dosing, manufacturing lines, managing machines, conveyors, and robotic arms, RO systems, ensuring proper water filtration and flow control, HVAC automation, regulating temperature, airflow, and energy efficiency, conveyor automation, moving products smoothly in factories and warehouses. In short, if there's a process that needs control and monitoring, chances are a PLC is involved. Can you think of any other places where PLCs might be used? Maybe in your home or workplace? Share your ideas in the comments. This brings us to the end of our PLC Basics session. In the next video, we'll dive deeper into PLC programming and advanced applications. Thank you for watching Instrulogic channel. If you like this video, please don't forget to like, share, and subscribe button.